Okay, it's time to begin. That's perfect. It's time to begin and the screen disconnects. So we go back to the hardwired one. How does that make any sense? Okay, so going over the record here, Amanda, Michael, Chad, who's still sick, Ann, Austin, Jaron, Haley's here, right? And James, they're not here. Okay, I'm going to finish thermodynamics and hopefully start in with some sound. I really hate to rush things, but we're now in the last week of the semester, and so it's getting to the point where I got to get these things in. As a few things in terms of grades, the lab finals, I believe, are graded. I don't know if the grades are uploaded or not. Okay, but I believe they're already graded. And I have started putting in the attendance bonus, and I have the pre-test and post-test grades in there. So those are now calculated in as part of your grade. So like, as of right now, just Michaela, Jerry, and Tori have their attendance bonus in there because even if they had been absent today, they still would have gotten the attendance bonus. And I will update for those who, by virtue of today, have it. So you can see that. I haven't started grading the test because we were interviewing that math guy, and I'm on the committee, and I've had a lot of time taken for that. But I will get the last exam graded by Thursday night so that by Friday morning you'll know exactly where you stand. And Bridget, wherever you are, I'll make sure I get that lab graded too. So you'll know where you stand as far as the final exam. The final exam is a cumulative exam covering everything in the entire semester. It will have a little more emphasis on these 2 weeks after the last exam, but it will be covering the whole thing. And you have to take, the scores on 4 of the 5 exams. So if you are happy with your grade based on the first 4 exams, then you don't have to take the final exam. But, if you want to take the final exam, it's never going to hurt you. It can only help you. Yes?
So would you like to know ahead of time so you know how many to print out?
It does help to not waste paper.
I figured.
Unfortunately, we don't have the function of projected final grades so you can see exactly what scores would translate to what grades, because that was really nice for students. That's not available yet with this version of Moodle. Okay, any questions before I get on to actual lecture? Nope. Okay then.
Real quick,
yeah, go ahead.
On the testing track, once we get the lab final inputted and the exam grade inputted, that will be a good grade for us to judge where we're at.
Yeah, I think that's pretty much it. There's, there will be one more homework assignment. Well, tonight is just turning the Flip Friday, which will be the last Flip Friday. There won't be a Flip Friday this week. It'll be a review lecture. And there will be a homework assignment due on Wednesday and one on Friday. But your homework grade shouldn't change much from one assignment. I still have to grade, by the way, your calculus one. What about tomorrow? There is a lab tomorrow. Is that what you're asking? Yeah. Yeah. Okay. First, a clicker question. What is the purpose of a heat engine? You've already seen this question, but just making sure it's still in your head. Okay. everyone that's here has answered. Woo. Answers are slowly moving toward the correct answer. That's good. Maybe if I would have waited, we would have had the final person switch. The purpose of a heat engine is to convert heat into mechanical energy. That is, to allow us to use heat to produce work. So that's the whole goal, and we've talked a little about heat engines. I hit the wrong one for forward. Here is a simple piston engine, and you have work done on the engine, that is the work coming out, I should say work done by the heat engine on whatever is out there. You have a gas that you heat. What happens to a gas that you heat? Remember, we have PV equals NKT. That doesn't have heat in it. But when you heat a gas, what's going to happen to the gas? Okay? It will expand or the pressure will increase. Now, if it's a monatomic ideal gas, that is a gas with one atom per molecule, then we can actually say that the internal energy is only the kinetic energy. So we learned that the kinetic energy average was equal to 3/2 kT. So the internal energy for monatomic ideal gas will just be the average kinetic energy times the number of molecules. So for a monatomic ideal gas, the internal energy, so I don't have it written here. I know if you watch this on YouTube, it'll have the words, but it's good to have for monatomic ideal gas. The internal energy is 3/2 NKT. So when you increase the temperature, you increase that internal energy, or in terms of, well, you increase the internal energy by putting heat in, and that increases the temperature. That's what I meant to say. So you put the energy in, you're going to increase the temperature if it's a monatomic ideal gas, and then that will result in either the pressure going up or the volume going up. So you have this piston, you put in the heat, which raises the temperature, which makes either the pressure increase or the volume increase. And in reality, what's going to happen? Well, first the temperature goes up and the pressure shoots up, and then it expands because it takes time to expand. And as it expands, then you have the volume increase and the pressure drop back down. And so during that expansion, you have work is equal to pressure times change in volume. So the volume's increasing, you're having work done by the gas. So you put the heat in, and then work was done. Now, ideally, that would be the end of it. Ideally, I put heat in, and work is done equal to the heat. But in reality, I can't just take all of that heat and convert it into work. Instead, I'm going to actually have to exhaust some heat. I'm going to have to drive out some heat, but at a lower temperature. And so this piston comes back generally and blows out your cooled now gas. So that's how you're actually getting work out of this heat engine. You put heat in, it expands. This equation here, the U equals 3/2 NKT, was only true for monatomic ideal gas, but the principle still applies for all gases. That is, you increase the internal energy and the temperature is going to go up regardless of the type of gas it is. It's just how it's related that changes. Now, we've talked about isobaric and isochoric processes. What's the difference in an isobaric and an isochoric process? Okay, isobaric is constant pressure, isochoric is constant volume. So we've talked about those two. Here I have two more processes, one in red and one in, well, they're both in red. Isothermal and adiabatic. Isothermal, iso means same, so we have that part down. And the thermal means temperature. So isothermal means the same temperature, constant temperature transition. Contrast that with adiabatic. Adiabatic means no heat. Does that make sense to have two different things, one called no heat and one called no change in temperature?
Technically, if you're melting something, that's still be isothermal, right? But it wouldn't be adiabatic.
Okay, if you're melting something, it's isothermal because you're putting heat in and the temperature staying constant. That's a great example. So it is possible to have temperature constant but not heat zero, or to have temperature change and heat stay constant. So the two things are different things. We often think of them like they're the same because we had things like Q equals mc delta T, right? That we put heat in and the temperature changes. And so we think, okay, so if temperature doesn't change, there's no heat. But that doesn't have to be the case. Some examples of adiabatic processes. Have you ever seen like a video of an aircraft flying over water and it makes a cloud with it? Okay, Cassie has seen one. For time's sake, I'm not showing one. But it's really cool, and what's happening is you have this aircraft that's flying over water that is essentially saturated. That is, the air has as much water in it as it can hold. And when the airplane passes, it has a shock wave that's going out through the water, or through the air, and it's changing the pressure really quickly. So quickly that heat can't flow in or out. And what's happening is, behind the shock wave, you get a cooler region. It can't hold as much moisture. That's right behind the shock wave. And because it can't hold as much moisture, you have water droplets forming. And so basically you're seeing the backside of the shock wave because you had a very rapid transition too fast for heat to flow in or out. The same occurred, I mentioned to a number of people, taking a soda bottle, taking the lid off, and having a sudden freezing of what's in there. It froze quickly because there wasn't enough time for heat to flow out, and it rapidly expanded so its temperature dropped with no heat flow. So we can make adiabatic processes simply by making things go super fast so there's not time for heat to flow, or we can have really good insulation. Two ways of making an adiabatic process. Now, here we have a graph showing an isothermal versus an adiabatic process. And as you notice in the graph, the isothermal line is higher pressures than the adiabatic line. And since work is, how does work relate to that graph? It's the area under the curve. Then we would easily say, well, there's a bigger area under that isothermal curve than there is under the adiabatic curve. So if you are going through the same change in volume and started at the same state, you have to have both of those statements here, then you're going to have more work done by the isothermal process than by the adiabatic process. And here I've actually shown the equations for the two. You get those equations through calculus. Right? They're not things we can just do otherwise. Now, why are those important? Well, when we talked about heat engines, we talked about these processes. So just a question to make sure we understand these names, and then we'll talk about how it applies to heat engines. What is a process where that's supposed to be no heat, not heat? No heat transfer occurs. Okay, my answers here were 4, 1, 2, and 9. The 9 here is a majority of the people who answered. Actually, it might be the majority of people here, so we have 1, 2, 3, 4 absent. 4 absent means, no, it's not a majority. We had 9 that said adiabatic, and that's correct. Adiabatic, no heat flows. Okay, so now why is it important? The second law of thermodynamics is an important law that we've talked about many times, and I think I've given you multiple statements of it. One statement, heat always flows from higher temperature to lower temperature. Another statement, every process occurs to have as a net result an increase in the entropy of the universe. Now I say of the universe. If you have an isolated system, that is one that's not exchanging anything with the universe, then it would also be true inside that isolated system. Those are two statements of the second law of thermodynamics. But another version of that statement is that you are always going to have a heat engine that cannot perfectly convert heat into work. It always has to have some waste heat. And so we're going to look at first the Otto cycle, named after a German dude whose last name was Otto. This is the cycle used in a 4-stroke engine, such as is typically used in an automobile. AUTO, a completely different word, so it's just an odd coincidence that they're the same. We have a 4-stroke cycle in your car engine if it's a gasoline engine. If it's a diesel engine, it's a different cycle. But that car engine is a heat engine. So if we look at the cycles, we have first here the intake. During that intake, the piston is moving down and it's pulling air into the piston. So since the piston is moving, or into the cylinder, since the piston is moving down and air is being pulled into the cylinder, what's happening to the volume available? It's going up. So we can look and we can say, I don't see what's happening to the pressure if we have it open to the atmosphere. It should be constant. So we should have a constant pressure volume expansion. It's not shown here because they wanted to show just the important parts. So this right here, the red line, is the intake. Went to larger volume. Then we have the compression. Now the piston comes up. The valves have closed, so it's now closed. It's not going to stay at atmospheric pressure. If you decrease the volume, but keep the number of gas molecules the same, what's going to happen to the pressure? It's going to go up. So now we can say, aha, during this compression cycle, it is going up in pressure as the volume decreases. So here's my compression cycle. Then we have the power. The power is an instant. That's, well, it's not in real life, right? That's not possible. But in terms of our diagram, it is. In our diagram, we say, ooh, at this moment, I had ignition and the gasoline burned. Now, when we put gasoline in our cars, what's one of the things you always pay attention to when you put gas in your car? The what?
Right gas.
The right one. And how do you determine if it's the right one?
Cheapest.
Okay, Reagan and I are in cahoots here, although that may not be the lowest cost. But I do always go with the cheapest because I'm afraid of spending too much. What is your method, Alexis?
I don't want to put diesel in my car.
Okay, I don't want to put diesel. My sister's father-in-law did that. They had the wrong nozzle on the diesel. Right? Diesel is always supposed to have a green nozzle. Black nozzle is gasoline. Okay. That, of course, ruined the car engine. Motorhome in this case. Okay, so you don't want diesel. What do you guys look for? Ryan, what do you look for when you're buying gasoline? Besides price.
Ethanol content.
Okay, ethanol content. You guys have a lot of chemistry background. Does ethanol burn?
Yes.
Yes. How much energy per unit volume do you have in ethanol compared to gasoline? Less. The ethanol has less energy per gallon than gasoline does. So if you have 10% ethanol, that means you're getting less energy per gallon, which is part of the reason why buying the cheapest gasoline may not be the best choice, because you're getting less energy with that money. The ethanol gasoline would be more expensive, but for the government subsidizing it, who's getting that subsidy? Nebraska corn farmers, right? So Nebraskans tend to be happy about that. Okay, so that's another thing, looking at the energy content, looking at the amount of ethanol. There's one final thing that no one's mentioned. The octane level. What's the octane level? Y'all have chemistry. What does octane mean? You have 8 carbons in your hydrocarbon chain. That's what octane means. The octane level is actually pretty complicated in its true calculation, but it's in essence, the idea is measuring how much you have long chains longer than 8 oxygens, longer than 8 carbons in your molecule. Why does that make a difference? Longer chains take longer to burn. Shorter chains burn more rapidly. And so higher octane means your burning takes longer time. You're buying longer burning gas. That's actually beneficial because when that spark plug fires, if you have a low octane number, it's going to burn really quickly. And so it's going to have the temperature go up much more rapidly with the low octane number, meaning that it tries to expand much quicker. It's kind of like taking a hammer and hitting that piston head. Whereas if you have a higher octane number, it burns more slowly, the temperature goes up more slowly, and it pushes a little easier starting on the piston, and so you're less likely to have what we call knocking. Knocking is actually when you hit the piston so hard that you have something that tilts, which is bad, right? So that's what the octane thing is all about. If your engine is knocking, one way to stop the knocking is go to a higher octane. Another important thing you might do is make sure you have enough oil in it. Okay, so here we have the spark. During that spark, boom, the pressure goes up really quickly because we just burned all that gas. And then we have the expansion, and the expansion here is actually what they show as the power stroke, because the power stroke is when that high pressure gas now is pushing the piston out. So this here in black is our power stroke. And then the final stroke is going to be exhaust. So now this one here again looks a little confusing. You get to the end and you open up a valve. The pressure's still higher than atmospheric pressure. You open the valve, and as soon as you open the valve, a lot of gas comes out. And so that's what happened here when you open the valve. But then you have the piston go up to push the rest of the gas out. And so this exhaust is actually these two things that I put in magenta. Opening the valve has most of it go out, and then you have pushing it out. So that's the Otto cycle. That's what's going on with an automobile engine. How can we measure the amount of work that comes out from this graph? Yeah, we do the area between those curves, just like you did in a homework problem, right? Speaking of homework, just to make sure everyone heard me, I said this at the end of class on Friday. I had the change in entropy, or not the change in, the actual entropy on the wrong line there on the sheet that I gave you on Friday. It was the second non-zero, or it was the second one, and I took the second on, I put it on the wrong line. It was off by 1. And I'm sorry for that. Did not intend to confuse the class on that, which is why I told everyone there at the end of class when, I think it was Alexis pointed out, wasn't it? Alexis, Lindsay, somebody like that? Okay. Any questions on the Otto cycle here?
At the very end there, the volume is staying constant when we open our exhaust valve. What is it, the volume of?
It's the volume that is in the cylinder, yeah.
Of the cylinder?
So it's basically from the head down to the piston.
So I was thinking, once you open the exhaust, then you have that entire, from the top of the cylinder all the way out to the world.
Yeah, we're not counting the other parts. Okay, now notice we had two adiabats. The expansion and the contraction were listed as adiabats here in the Otto cycle. That's a, shall we say, optimistic interpretation. Heat can't flow if you go really quickly, and so it's saying, well, the piston moves up and down so quickly compared to the rate that heat flows that we can treat it as roughly adiabatic there. Now let's move from the Otto cycle to, I can't believe I didn't delete that one, to the Carnot engine. The Carnot engine, designed by Sadi Carnot, although if you looked at the questions I had and stuff, he has two other names before Sadi. This is a special engine that is a reversible engine. First thing you have to know about reversible is it doesn't exist. Reversible means you could run it forward or backward just the same, which would mean that you have to have a net change in entropy of 0 for that to occur. But in practicality, we can't make a reversible engine. The textbook says it would have to take longer than the age of the universe to do one cycle for a Carnot engine. Hence, we can't make one. So this is a theoretical ideal engine. And you might say, what is the stinking point of having a theoretical ideal engine that we can't make? The point is that it gives us a target to shoot for. Theoretically, this ideal engine, the Carnot engine, gives you the best possible efficiency you could ever have for a heat engine. And so we look at it. The Carnot engine has an isothermal expansion followed by an adiabatic expansion, then an isothermal contraction followed by an adiabatic contraction. With this cycle, when you have an isotherm, the temperature is not changing. Okay, so that means that, well, I'm not going to focus on that one. I'll focus on the next one. When you have the adiabatic conversion, you have no heat. Well, an equation that's going to be coming up says the change in entropy is equal to Q over T. Now, that equation was technically for only a certain case, but in practice, we can use it all over the place. And so, for an adiabatic expansion, there is no change in entropy. In fact, there is an alternate name for an adiabat, and that is isentrope. An adiabatic process is isentropic because the entropy stays the same. So we have no change in entropy on those two pieces. We have no heat as well, so that means that the change in internal energy is minus the work. Going through calculations that we clearly won't do for time today, it turns out that for a Carnot engine, the heat is proportional to the temperature. On which ones of the cycles, or which ones of the processes in the cycle, I should have said. On which processes is that true? If you think it through, it will become clear. And thus I'm asking you to think it through. This is rough. Would that be isothermal or adiabatic? What was our last clicker question? What was our last clicker question? Yeah. Which one is no heat transfer? What was the answer? Adiabatic. So if adiabatic has no heat transfer, which process does this have to be for? Which one? There are only two types of processes here. Adiabatic and isothermal. So by a process of elimination, if I take adiabatic and isothermal and say it can't be adiabatic, then it must be for the isothermal. Right, so I have a heat during the isothermal expansion that's proportional to the temperature of that expansion. It's kind of good that that's the one, because if you had a changing temperature, you'd say, well, how do I work the proportionality? Then I have the adiabatic process, which has no heat. Then another isothermal that's going to be proportional to the heat, proportional to the temperature, and the final adiabatic. So what does that allow me to do? It allows me to calculate the efficiency based on the temperature of my cold reservoir and my hot reservoir. So the efficiency can be written as 1 minus the cool heat divided by the hot heat. And so making that substitution that heat is proportional to temperature, since heat is proportional to temperature, if I'm dividing the two heats, that would be equal to dividing the two temperatures. Right? If I just had heat by itself, I couldn't make that substitution. I still have proportionality. But because I'm dividing, the constant proportionality divides out. To make that clear, this is like saying Q is equal to some constant multiplied by temperature. So Q1 over Q2 is equal to A temperature 1 over A temperature 2, and the A's cancel. So that allows me to get the efficiency in terms of temperature. Now I can look at this and say, what temperature difference, or what cold temperature, or what hot temperature would give me the most efficient theoretical engine?
Cold temperature of absolute zero.
Okay, having the cold temperature of absolute zero. If the cold temperature is absolute zero, and note she said absolute zero. 0 Celsius, that's 273.15. You have to use kelvins here. 0 Fahrenheit, I don't remember what it is, but it's not zero. But at absolute zero, that would be 1 minus 0. You'd have a perfectly efficient engine, if the ideal engine was possible, if your cold temperature for the exhaust is 0. Yes?
Can you have a high temperature of infinity?
If you had a high temperature of infinity, you would achieve the same goals. So the bigger the temperature change, the more efficient it's going to be. The colder the cold temperature, the hotter the hot temperature, the more efficient it's going to be for the ideal engine. But then we come back to, what was the point? This isn't a real engine. I can't make this engine. So what's the point of even knowing this? It tells me what I can shoot for. I should have let you answer. My bad. It tells you what you can shoot for. What do you suppose the efficiency is for a typical automobile engine?
Probably really bad.
Yeah, it's probably really bad. We could calculate the ideal efficiency of an automobile engine. If we know the temperature at which the gas burns, that would be the temperature hot. We know the temperature of our exhaust, that would be the temperature cold. And we could calculate a theoretical maximum. And I believe that car engines are somewhere in the ballpark of around 50% of that. Car engines, I think, get around 30% efficiency. But what you do is you look at how close are we to the optimal efficiency, because, if you're at 98% of efficiency, 98% of optimal, it's probably not worth your time trying to design a more efficient engine. But if you're 50% of optimal, well, you've got some room to improve. So a car engine that burns hotter would, in theory, be able to be more efficient. A car engine that has a colder exhaust temperature would, in theory, be more efficient. So those are things to shoot for in designing the automobile engine. Even though it's the Otto cycle, not the Carnot cycle, we will still have, that general behavior. Yes?
And that's going to be the exhaust right out of the output of the cylinder.
Yes. It wouldn't be when it gets out of the tailpipe. It'd be when it comes out of the head, yeah. So you'd measure the temperature of the exhaust manifold. Okay. A few final things here on heat engines. Here is a typical way of producing electricity. You heat up water, and that water produces steam. Where I started with the heat engines on Wednesday, that heat then is used to drive turbines, basically big optimal windmills, and those turbines turn electric generators that we'll learn about next semester. So that's where you're getting your electrical energy from, this turbine generator. Well, then you have a lot of hot steam. You need to cool it back down. So you have these cooling towers that come with your power plants because you need to cool it down. Now, if we look at some photographs here, here's a picture of a nuclear power plant. Here's a picture of a coal power plant. You notice they have identical looking cooling towers because they're both simply heating up water. One is using nuclear fission to heat up the water. One is using burning things to heat up the water. But they're both heating up water, making steam that drives a turbine to generate electricity. Now, I have here a picture of San Onofre nuclear power plant down there north of San Diego. Notice there are no cooling stacks here. Why is there no cooling stack? Ocean water. Usually we like to make power plants close to bodies of water that we can use for cooling instead of having to have the cooling stack. So oftentimes nuclear power plants are built along waterways because you have a lot of cooling you need, and you do not run water from the steam that's driving your nuclear power plant out into your body of water. You run, as is shown in this picture, an isolated water system. So you just have cool water from the ocean that comes in here, hot water that goes back out to the ocean, but it's isolated. So you don't have radioactive water running out into the ocean. Now, from a philosophical and ecological standpoint, this is not perfect using the ocean or using a river. Why not? Yeah, you're heating up the environment. Whether you're dumping sewer into the ocean, which we all do, I'm not talking about on individuals, I'm talking about municipalities that are built along the, it's kind of sick to think about, isn't it? Because we go swimming at the beaches, they run a pipe like, X miles off the beach and they dump sewer out there. Whether you're dumping sewer out there or using a power plant, you're going to be changing the temperature. You change the temperature, you change the ecology. Things like damming up a river. We have Hoover Dam, Lake, Mead, isn't it? Behind it? Or Powell? I get confused. Lake Havasu. Completely changed the ecosystem of the end of the Colorado River. And so some animals can't live there anymore. Others move in because it's ideal for them. But people get really concerned because that's humans changing the habitat for the animals. And I am not going to say yay or nay over whether we should do this. I'll leave that to the Sierras Club and other people to make their arguments. But it is something to think about. Yeah.
I mean, like that with a nuclear power plant cooling into the ocean, that's a statistically significant amount of warming.
Yes. Yeah, the temperature is, I don't remember how much, but it's at least a few degrees warmer because of that.
For the world's oceans?
Well, no, for the local area. Yeah, for the world's oceans, no big deal.
There's a lot of water.
Yeah, it's for the local ecology, just like with a dam. And while I'm on this, what are other ways that we produce energy? We've talked about nuclear, coal, solar, wind. What other ones? Well, we're finding ways of producing electrical energy in general. What'd you say?
Natural gas.
Okay, natural gas. I'm gonna just stick all of the burnings together as one. Okay, hydroelectric, geothermal. Okay, that's enough. That's a good group of them. None of these are perfect. Each one has its own ecological problems. Take, for instance, windmills. Windmills seem like a great way to generate energy. But they do a couple things. Number one is they're unsightly. Well, that's just for humans who have a sense of aesthetics. But number two, they make sound and vibration which disturbs animals. Number three, they chop up birds that aren't smart enough to not fly through them. Right? So they do cause problems to the environment. And so that's something that has to be weighed. We talk about solar panels. Solar energy really seems like a no-brainer. We have so much solar energy. Right now, it's costly to harvest that solar energy. There are a couple of different methods that have been developed to harvest it. One of them that I usually show a picture of, you have a whole bunch of mirrors that are computer controlled so they'll reflect the sunlight on one big metal ball. And then that metal ball has a sodium slurry in there. Why sodium? Because of its thermal properties, specific heat and whatnot. That gets melted and then gets pumped down and goes to a heat exchanger to produce electricity in the standard steam method. It's a really efficient method. Well, really, compared to the other styles where you have the little photovoltaic cells. But it has some problems. Problem number one, what temperature do you suppose it is up there near that ball? It's hot enough to melt sodium. It's super hot. Birds come flying by. It's much like Icarus. Got too close to the sun and got melted. Right? So you're once again harming animals. And so that's a downside. Sodium is no fun to play with. If you have a crack and water gets into your sodium, then what happens, friends?
Go light some fire.
Yeah. It's really exciting. You make the photovoltaic cells. Photovoltaic cells, there's a lot of pollutants that go into making a photovoltaic cell. Nothing is perfect. Everything we need to evaluate and try to find the best compromise. Either that or go off and live by ourselves with no power. I am a sucker for power usage. By the way, I brought this demonstration with me because it's totally cool. You might have noticed in the book you had a picture of the little dipping bird that I always found really obnoxious. This is basically the same thing, but much simpler. I have this liquid in here, and I put my hand over one side, and I say, "Mwah." And look, isn't that wonderful? What happened? What happened?
You heated up the gas and we expanded and pushed the water on the other side.
I heated up, well, not just the gas, I heated up the liquid, and the liquid has a boiling temperature that's a little lower than my body temperature. And so I made the liquid boil, and the higher pressure that was produced in the gas then pushed the fluid across. So if I now heat up this side, I can push it the other way. Totally cool, right? That's also a heat engine. Not very useful. I'm not getting anything out of it, but it's fun to play with. Okay, let's go to heat pumps. So heat pumps are heat engines run in reverse. For a heat pump, you're putting work in to move heat. In my mind, a heat pump is just a conveyor belt. A conveyor belt, I put gasoline in the engine, burn that gasoline, that's the work that's going in there. Work is produced by burning gasoline. And then I could be putting like coal on one side of the conveyor belt and it moves the coal from one side to the other. That's what's going on with the heat pump. You're making the heat move. Now you might wonder, what's the purpose? Well, the purpose is that heat naturally flows from what temperature to what temperature? High to low. But using a heat pump, you can essentially make a conveyor to make heat flow from low to high temperature. And so your idealized picture, you have heat at a cold temperature goes in, and work goes in and those combine to exhaust heat at a high temperature. Now you could use this heat pump for two purposes. One, to extract heat at a low temperature. That would be an air conditioner or a refrigerator. The other one would be to exhaust heat at a high temperature, a heater. So heat pumps can be used either as a heater or a cooler, which is great. You set up a heat pump in your home, and when it's hot outside, you set it so you pull the heat out of your house and exhaust it outside. When it's cold outside, you just reverse the connections, and then it's going to take heat from outside and pump it inside. So a heat pump can both heat and cool your house. That sounds marvelous, right? The problem is they're not very useful if you have a big temperature difference. They work the best at small temperature differences. It is not converting something into something else, right? The heat engine was converting heat into work. This is not converting work into heat or anything like that. It's simply using work to transport heat. So we can't really calculate an efficiency. Instead, we calculate a coefficient of performance. And so if you're heating, the coefficient of performance is going to be the thing you are interested in, the QH, because you want a lot of QH if you're heating, divided by the work you put in. And of course, using our first law of thermodynamics, that's just QH over QH minus QC. If you used a Carnot engine, that would be TH over TH minus TC for the ideal Carnot engine. For a typical household heat pump, you get about 50% of the actual Carnot coefficient of performance. The Carnot coefficient of performance is somewhere 4 to 6, so your actual coefficient of performance is somewhere in the ballpark of 2 to 3. But when you think about it, a coefficient of performance of 2 to 3 means that you're getting 2 to 3 times more heating than the energy that was required. If you were burning gas, how much heating would you get out of that gas? All of it. Right? You burn the gas, all that heat comes out, and that's your heat. So you would have a coefficient of performance for burning gas of 1. Whereas using a heat pump, 2 to 3. So it seems like the heat pump is a no-brainer. There are some drawbacks. Number one is the heat pump usually runs on electricity. And electricity is more expensive than gas. So it's not a 2 to 3 times savings in dollars. It's only a 2 to 3 times saving in energy. And, well, I see people putting their stuff away. I'd better move on. This diagram over here is showing how the heat pump actually works. How you can make heat go the opposite direction that it would naturally go. So I'll start on the left side where it has the evaporator. You have hot fluid, refrigerant if you will, that's in a tube. And then that tube, oh wait, no, this is the wrong side. Let me start on the condenser side. We have hot material on the condenser side. You can tell by the colors. The red side is the hot and the blue side is the cold. You have hot material there in the condensers, and then you have air flowing by. Well, the air is going to, by convection, remove heat. And so that hot material that went into the condensers, it starts here very hot and comes out here at room temp. And then it goes through an expansion valve. I allow my gas to expand rapidly. Expand rapidly so there's no heat. What happens to the temperature of a gas if you allow it to expand rapidly with no heat flow? If it expands, we had work go out. So the internal energy goes down, so the temperature goes down. So it cools, and so we suddenly have going from room temperature to having a cold gas on this side. And then we go through the evaporator where we have heat from the cold side, warms that refrigerant up. So here I'll put cool. It's not room temperature yet. Well, it depends on if you're a refrigerator or a household cooler. But it's cooler there. Then you have a compressor that pumps it. That's putting work in, compressing it. And so the temperature shoots back up to make it hot. And so what you're doing is using the compression and expansion of gases to change the temperature one side to the other of the expansion valve and the pump, and then letting heat flow the way it naturally does from the hotter refrigerant out to the environment, or from the environment into the cooler refrigerant, to make heat actually flow the opposite direction that spontaneously flows. And I guess we will do sound next class period. This is my last non-sound slide, talking about entropy and statistics. You worked on this on Friday and the Flip Friday. Just want to make sure that we nail home a few of the ideas. As Jaron pointed out, usually we use omega here, but our textbook used W, so I use W. Entropy is, in fact, simply a measurement of how many ways you can stack things or place things. So if I have all of these napkins, or whatever you want to call it, there's lots of different orders I can have them still in a nice, neat pile. So if I calculate the number of microstates, that's how many different ways I can arrange them to still be in this state of nice, neatly stacked. If I take these and spread them out all over the table, there are a lot more ways I can distribute them and have them evenly spread over the table. So I'd have a lot more microstates in having these spread out over the table than in having them in a neat stack. And the probability of being in any state is simply how many ways can I stack it divided by how many total ways can I have them distributed. And so the most probable way of having them, which would be spread out on the table, is the highest entropy. And so it's really just a statistical law that says, like I said in the Flip Friday, the most likely outcome is what's going to happen. That's really the statement of the second law if you use the statistical interpretation. So, and I have to say this, in theory, all the molecules in this room could go up in the corner. What would happen to us? We'd die. That could happen. The second law says it's not going to happen because that would be going to a higher ordered system. It could happen, but the second law says it's not going to because it's not probable. This argument is used a lot when you talk about creation versus evolution. Creationists will say that evolution is a violation of the second law. That evolution says we went from a less ordered to a more ordered system. And the evolutionist will say, well, think about a human. A human starts as a little gamete and grows and becomes more and more complex. Certainly the entropy of the human was going down as it developed. But what was going on at the same time? We were exhausting heat in different forms, so the entropy of the universe was going up. And furthermore, they say for things like the creation of life out of nothing, abiogenesis, it could happen. It might be a 1 in 2 billion chance or 1 in, 2 Googleplexes chance. But it could happen. Second law says, yeah, it could, but it's highly unlikely. So it's not correct to say that the second law says evolution couldn't occur. But it is correct to say the second law says it's so unlikely that I don't think we should expect it to have occurred. Okay, have a great day. See you in lab mañana.